Today we are going to discuss the potential flow. Potential flow is a flow which is inviscid, meaning which has negligible viscosity, which is incompressible, that is rho equals to constant, and which is irrotational, in which we have del cross V equals to 0. Now let us see what is stream function and velocity potential. Stream function has been defined to verify the continuity equation. The continuity equation is du by dx plus del v by del y equals to 0. Stream function is basically denoted by psi. So in stream function, u equals to del psi by del y and v equals to del psi by del x. It has been defined like this. Now putting this in the continuity equation, we have del x of, instead of u you are putting del psi by del y plus del y of, instead of v we are writing del psi by del x. There is a minus sign over here. We'll put a minus sign here. It has been defined like this. Now on solving this, we find del square psi by del x del y minus of del square psi by del x del y equals to 0. This satisfies the continuity equation. This satisfies continuity equation. Now we define velocity potential denoted by phi. Velocity potential, it has been defined such as to satisfy the irrotational condition. Defined to satisfy irrotational condition. Here u equals to, like here we had u equals to del psi by dy, now del y. Now here we'll have u equals to del phi by del x and v equals to del phi upon del y. The irrotational equation is del v by del x minus of del u by del y equals to 0. Putting the values of u and v in terms of psi, we have del x of, instead of v we are writing del phi upon del y minus of del y, instead of u we are writing del phi upon del x. We can see that this turns out to be 0 again. So we can say that stream function has been defined in order to satisfy the continuity equation, and velocity potential phi has been defined in order to satisfy the irrotational condition. Now let's see what happens if we'll put the value of psi in the irrotational condition. So irrotational equation, the irrotational equation was v upon del x minus of del u upon del y equals to 0. Putting u and v in terms of psi, del x of, instead of v we are writing minus of del psi upon del x, del y of, instead of u we are writing del psi upon del y. Now we are equals to 0. On solving, we are getting del square psi upon del x square plus of del square psi upon del y square equals to 0. This can also be written as del square psi equals to 0. This is the Laplace equation where del square equals to del square by del x square by del square upon del y square. Now again let's see what happens if we put the continuity equation in terms of phi. So we had the continuity equation del u upon del x plus del v upon del y equals to 0. In terms of phi, we will have del x of, we had u equals to del psi upon del y, v equals to minus of del psi upon del x, phi equals to, u equals to del phi upon del x and v equals to del phi upon del y. Putting the value of u in terms of phi, let's see what happens. Del phi upon del x plus of del y of, instead of v we'll write del phi upon del y equals to 0. This turns out to be del square psi upon del x square plus del square psi upon del y square equals to 0. This can also be written as del square psi equals to 0. This again is the Laplace equation. This satisfies the Laplace equation where del square equals to del square by del x square plus del square by del y square. So we can see that if we put u and v in terms of psi in the irrotational condition, we will get the Laplace equation. Again, if we'll put u and v in terms of phi in the continuity equation, we will get the Laplace equation. But if we'll put the value of u and v in terms of psi in the continuity equation, we'll get the value 0. Means stream function has been defined in such a way such as to satisfy the continuity equation, and velocity potential has been defined in such a way such as to satisfy the irrotational condition.